We'd like to welcome Boyan Kostadinov from New York City College of Technology, presenting hitting a stationary target by firing a projectile from different angles.
Thank you. Now, this project is about an inverse range problem, in fact. And in this talk, we consider an inverse range problem for projectiles whose origins are attributed to Niccolò Tartaglia, a self-educated mathematics teacher, engineer, and surveyor from the 16th century Republic of Venezia. His writings had a big influence, in fact, on Galileo, who owned a richly annotated copies of Tartaglia's works on ballistics. Now, Tartaglia was selling mathematical advice to gunners, and one of his findings was that the maximal, that is the optimal range of a projectile fired from a cannon, can be achieved by directing the cannon 45 degrees relative to the horizon. But another claim attributed to Tartaglia was that any given suboptimal range can be achieved by firing the projectile at two different angles. Now, the inverse range problem that we're considering can be stated as finding exactly these two firing angles that lead to the same suboptimal range, accounting for air resistance, however, not in the sort of idealistic model without any air resistance. Now, in fact, so we develop a computational framework for this project based on the R programming language and RStudio for this inverse range problem by considering a model of air resistance where the air drag is proportional to the velocity initially, sort of a linear model of air resistance. And we'll also discuss further extensions to more general models of air resistance where the air drag depends on some power of the velocity. And these are the really realistic models that can capture some real data. Now, I'll start with the projectile problem with linear air resistance. So what you see here is the vector differential equation for a point mass in the gravitational field of the planet, assuming linear air resistance. Here, let me go over quickly the notation. So anything in bold is a vector. M, of course, is the projectile mass. The R is a function of T, that's the projectile radius vector. G is the gravitational constant. J is the unit vector in the positive upward y direction. K is the air resistance parameter, and V is the velocity vector along the tangent to the projectile directory. Now, the vector equation can be decomposed into an equivalent scalar system along the x and the y directions, where the center of the Cartesian x-y coordinate system is located at the point the projectile is being fired from. So what you see here is the equivalent scalar system where the dot represents a time derivative. And this is in the linear model of air resistance that we're considering now. So we can integrate the second order system of ODEs twice by first integrating the system with respect to the velocity components. And that's the system that you see here in terms of the V's. These are the velocity components along the X and the Y directions. And then we can integrate one more time using an integrating factor and initial conditions and time 0. Assuming a projection angle of theta between the initial muzzle velocity v and the x-axis. So here the notation is that v at 0, that's the velocity at time 0. The initial muzzle velocity is given to be v. Then the x component of this velocity would be simply the orthogonal projection on the x-axis. So it's just v times cosine of theta. And the y component would be the orthogonal projection along the y-axis, so it just be seen sine of theta. And the position is at the center of the coordinate system. Now, the projectile model with linear resistance actually has an analytical solution, and that would be a great exercise for students to derive this analytical solution by integrating the original system twice. And an integrating factor can be used to complete the integration. So it's a nice exercise of sort of integrating the original system in the case of linear resistance, where you can get these analytical solutions for the x and the y positions as functions of time. And so we can solve for time in terms of x from the first equation, the expression for x, and then substitute back into y to get y as a function of x that is given here. Now, for the projectile range, so let's say the projectile range is represented by x sub r for the range, the x position. To get it, of course, we need to set y to 0. And this gives a nonlinear equation for the range that you see here in terms of the logarithm. But the logarithm is difficult to work with numerically because solving this equation would have to be done numerically. And this could present all sorts of issues for students trying to implement a numerical solver. So it's much easier to actually exponentiate the equation and deal with the exponential functions instead of the logarithm function, where you have to be careful about the domain of the logarithm function to get everything right. But now with the exponential function, the last equation that you see here for the range xr can be solved numerically. And this nonlinear equation can be solved numerically using Newton's method even, because you can compute analytically the derivative. So that makes it a good example for implementing Newton's method. Even the bisection method, could be used. But the way we did it was actually using a fixed point iteration, which is another great, because this is a great example to sort of implement a fixed point iteration. That would be a great exercise for the students to play with. And so we can define the right-hand side of the nonlinear equation in terms of this function f of x that you see here on the top of the slide. And basically, we want to solve the equation x equals f of x. That's the equation that we need to solve to find the range. And that's really a fixed point iteration by starting with some initial guess and then iterating the function f to find a fixed point. Let's call it x sub r, which is positive. Now, a good initial guess for the iteration can be the range that is based on the formula for the range without air resistance, which is the initial velocity squared times the sine of twice the projection angle divided by the gravity constant. But fixed point iteration can be implemented numerically by the students, and that will be another good computational exercise. So the next value basically of the approximation would be the value of the function evaluated at the previous approximation. And for some sample numerical values for the velocity, 100, that's 100 feet per second, air resistance constant K of 0.1 and an angle of approximately 0.43 radians. I showed here the beginning of the iteration, starting with the initial guess, which would be the range without air resistance, 235 feet. And then ending with the tail of the iteration, I did 100 iterations, and then you can see that basically x is converging to the number 200. Now, of course, in general, the sequence x may or may not converge. However, if the function is continuous, and it is in this case, and the sequence converges to some number, then this number is indeed a fixed point. And one good way for the students to see a convergence numerically is to sort of show the iterations at the tail of the fixed point iteration. And if there is a sort of if the numbers converge to a given number, like in this case 200, that's sort of a numerical way, of course, to see convergence, which is a good way to build intuition. And that also suggests that this is a fixed point. Now, the fixed point iteration can be explored. This is a great area to kind of a good playground where one can even visualize the fixed point here. What you see on this graph, the graphs of the function y equals f of x, as well as the graph of the function y equals x, and the intersection point is actually the fixed point, and you can see that the intersection point is exactly 200. So that's the range. Now, one can also compute the derivative of f analytically and investigate the absolute value of this derivative, because as you know, if the absolute value of the derivative function is strictly less than 1 in some interval around the fixed point, that sort of guarantees the linear convergence of the fixed point iteration to the fixed point, let's call it R, for any initial guess that is close enough to R. So this is a rich playground for numerical implementations of a nonlinear solver using the fixed point iteration, or even Newton's method would be a good exercise, because we can compute the derivative analytically. Now, in this plot, so now that we actually implemented a function, a range function, as a function of the firing angle theta. So we plotted here the graphs of the range as a function of the firing angle for different values of the air resistance. So on the top K, 0.1, then 0.2, and so on. So from these graphs, of course, it's clear that for any given range, so in particular, I was playing with the range 200. So you can if you go horizontally along at the level of 200, you see, of course, that there are 2 points where the horizontal line intersects the graph, and these are the 2 angles that would produce the suboptimal range of 200 feet. And the first angle you can see approximately is around 0.43 actually radians, and the other point here is a little bit more than 1 radians, actually 1.03 radians. So this is a good way to kind of visualize the range as a function of the angle for different values of the air resistance, and to see what happens. And all this, of course, requires a numerical implementation. And I'll mention something about the technology framework for the numerical implementations of all the functions, because this is obviously crucial for implementing this project. Now, and now we are ready to get the 2 angles for a given suboptimal range. So having implemented the range function as a function of the firing angle, so we can implement, for example, a bisection method, because the function now is numerically defined, so we cannot compute the derivative analytically, but we can still compute the derivative numerically if one wants to explore using Newton's method. The bisection method is certainly a good way, or one can just use sort of a well-designed solver. And in particular, we're using an R solver for finding the solutions of a nonlinear equation. And then we can find the 2 angles, θ1 and θ2, that give the same suboptimal range. So for a given range R, basically we want to solve the equation, the range function as a function of the angle θ to be equal to this given range R, suboptimal range. And I'm using here for the numerical experimentation, I'm using the same, consistently the same numerical values. So the initial muzzle velocity of 100 feet per second, the air resistance 0.1, it has some units actually as well. Suboptimal range is 200, that's in feet. And so we get the 2 angles, approximately 0.43 and approximately 1.03 radians. And a quick check, of course, that the students can do is to evaluate the range function at these 2 angles and make sure that they do get 200. So you see 200 basically is being obtained in both cases. And finally, here is the a plot where you can see the trajectories of the projectile fired at these 2 angles that we computed numerically that give the range of 200. So you see here that the 2 trajectories, both at the 2 angles, hit the stationary target at the given range of 200. And that's pretty cool. But having a linear model of resistance, it's only approximately sort of a good model for very small velocities. So let's say maybe in the sports, if you're kind of trying to develop some models for projectiles used in sports, that could be a good model of linear resistance. However, if you want to have something more a more realistic model, let's say in the case of artillery projectiles, for example, then you need a more realistic model, and a more realistic model of resistance would be in general a power law model of air resistance, where and this is the vector differential equation for a more general power law model of air resistance, where the difference here is basically, this is the power term here that you see. So the velocity is to some power n, and that sort of generalizes, the linear model. Here in this notation, everything as before, except that the v hat here is a unit vector in the direction of the velocity vector, and v is just the magnitude of the velocity vector that is expressed here in terms of the x and the y components. So decomposing the vector equation into the x and the y velocity components actually gives you this system below for the system for the velocity for the x and the y velocity components. So you can see that this is a highly nonlinear coupled system of ODEs, and it has no known analytical solution. But it can be solved numerically, of course. And we implemented a numerical solution using the dsolve R package. And the solver, allows actually for many different methods to be used. It's state of the art, it's a professional grade solver. The default method is LSOLVer, which actually provides an interface to the Fortran ODE solver of the same name. Now, the implementation is still work in progress, the numerical implementation, even though I'm basically done with it and sort of managed to implement numerically the complete inverse range problem for this much more general model of power law model of air resistance. But I'm still trying to kind of finish this part of the project by finding appropriate numerical values to play with. So here what you see is the projectile directory with quadratic air resistance. And this is a numerical solution for the trajectory of a projectile in a model actually of quadratic air resistance. So like I said, I'm still sort of playing with the numerical values of various inputs. I'm trying to find realistic values. In particular, I'm really interested in finding some data based on the howitzer artillery shells. And this trajectory in particular that you see is based on using an initial muzzle velocity of 2,600 feet per second, which is around 800 meters per second, which is the range of the actual muzzle velocity of the howitzer artillery shells, and the initial firing for the initial firing angle of 60 degrees. And this is what you see. But then I played with adjusting the air resistance parameters K to get a range of around 75,000 feet, which is around 21 kilometers, because this is sort of the realistic range of the howitzer artillery shells, 20-something kilometers, and the height of around 44,000 feet, which is about 13 kilometers. And so when I was kind of playing to adjust these parameters, this kind of gave me an idea that it would be great to, if I can fit, in fact, the air resistance parameter and the power N in the model to some real data, if I can find some reliable data to do these numerical investigations. And let me sort of finish by mentioning something about the future investigations. Now, this is, as I mentioned, still work in progress. And I'm finishing now the numerical implementations for solving the inverse range problem for any power model with air resistance. Now I'm actively looking for real data based on the howitzer artillery shells, such as data related to, let's say, the maximum flight range, or any other relevant data I can find that would allow me to fit the air resistance parameter K and the power N to some real data, using least squares optimization. Now, this work actually has been done for an article I'm preparing for the IGMS special issue. It's to be published later this year on semiotic using modeling to motivate and teach differential equations. This is an active link that will take you to the special issue once it gets published in the IGMS journal. And finally, let me mention something a little bit about the computational framework, because this is an essential part of implementing this project. And from a pedagogical point of view, the implementation is crucial. And the computational framework for this project is based actually on Quarto notebooks, which are the latest generation of R Markdown notebooks that can be used in RStudio, either installed locally or on the POSIT cloud. RStudio renamed itself to POSIT recently. So this framework actually supports R, Python, Julia, Observable, and other programming languages that allow you to create publication quality, dynamic documents that combine code, mathematical expressions in LaTeX, And this can be used to support computational modeling with ODEs in the classroom and for student research projects or modeling with ODEs in competitions such as CUDM. Now, this technology that is based on our Markdown and RStudio allows us to create basically publication and professional quality project reports, lecture notes. You can create randomizable exams, presentations. This presentation is an example of a Quarto presentation. And even publication quality papers, blogs, and even websites. Now, a more detailed discussion of this technology framework and many computational examples in modeling with ODEs can be found in our Primus paper and online supplement that I'm happy to share. If someone is interested, this link, once the presentation is posted, you can click on this link to get to the paper and the supplement. But if you want, feel free to, if you're interested, feel free to send me an email at bkostadinov@cititech.cuny.edu, and I'm happy to share the Primus paper and online the code supplement with you based on a Markdown notebook. With that, I'll stop here. Thank you. I'm happy to take any questions if there are any.
I actually have a question. Have you used this project with students, or students helping you with the project right now?
Not yet. So basically, this started based on an invitation to submit a proposal to write a paper for the IGMS special issue. And this is a project that I've been kind of thinking for some time that it would be great to implement. And so I submitted the proposal, they liked it, and now I'm working on finishing the paper. And I guess this is a project that I will definitely implement with my students the next time I teach our mathematical modeling class, which has a big section on modeling with differential equations. But I haven't actually tried it yet. I'm still sort of experimenting myself. I'm basically done with the numerical implementation in the most general case for the power model and how to actually get the the two different angles that firing angles for the same suboptimal range. So I'm kind of done with that, but now I'm looking for some real data, kind of fit the model to some real data for howitzer artillery shells. I think that would be a good example where because they kind of have high enough speeds where a more general power model would be more relevant. But yeah, absolutely, I will. Of course, the goal is to actually try this with students. And the next time I teach our modeling class, I taught it last year. I hope to teach it again soon. I will definitely experiment this with students. But because I'm teaching all these other applied math classes where the computational framework is very important, and this is the same computational framework. So I do have a lot of experience with the computational framework in general in different classes that I've taught and in different student projects that I've used it. Any other questions?
Yes, I have a question. Thank you. This is really good talk and interesting work. So my question is about the R Markdown. I heard somebody else talking about it. I think yesterday or the before yesterday. I'm really interested in it.
Yeah, it's a great technology.
Yeah, your slides were nice. I assume you did
so
it.
These slides were created with Quarto presentations. I mean, if I can certainly. You probably don't have time now, but I can actually demonstrate on the cloud what everything looks like. But one thing that I can do immediately for you, if you send me an email to bkostadinov@cititech.cuny.edu, I'll send you this paper where we talk about this technology, and we give many examples as well as the online supplement and even I think I can find the actual notebook that generated, because each one of these documents was generated by an actual R Markdown notebook. So Quarto is actually the latest generation of R Markdown notebooks, and it's an amazing technology that offers native support for R, Python, Julia, Observable, other programming languages you can set up. It's very easy for the students to typeset mathematical expressions because you don't have the sort of the full complexity of a raw LaTeX document. I mean, I don't know, can you, let me actually, okay, let me show you very quickly. This is the cloud. Okay, this is the cloud. Okay, so this is another project here, but let me go to, let's say, one project. Which project?
Can I assume if our university installed, is that called CoCalc?
No, CoCalc is different.
Okay, so it can't be
CoCalc,
run there. It has to be done. Okay.
Yeah, right. This is specific to RStudio. So Posit Cloud now is the new name of what used to be called RStudio Cloud. RStudio changed their name from RStudio to Posit.
Okay.
So the Posit Cloud is basically, you can get a free account there immediately. They just ask for name and email. But I do pay $15 a month for the instructor account, which gives me the ability to create virtual classrooms. And I can create both an RStudio project as well as Jupyter notebook projects, but I prefer RStudio. I prefer the RStudio projects where I can run a Quarto notebook. So this is what a Quarto notebook looks like. There's actually, right. So there's no time, I guess, to spend too much, but this is a header, and then the rest is just plain text. This is a section header, then some plain text, then some R code, and you can run the R code by clicking on this play button. Then you can embed images. It's kind of like a plain text format, and that's why it's marked down, to mark down the complexity of markup languages like HTML and LaTeX. So it's very powerful. It's kind of like a fancy version of Jupyter notebooks, because you can create actually a publication quality project reports, even papers that I'm writing, research papers. I do everything in this framework using R Markdown and Quarto notebooks, basically.
I see.
It's very simple formatting. So there are a lot of resources. You can, the best thing to the fastest way to learn is just go to quarto.org, and that's it. That's all you need. You can find here on quarto.org. They have for Python, R, Julian, Observable right now. Things set up. So if you're interested in R, you can sort of start exploring all the documents. It's very well sort of prepared documentation, so you can learn very quickly how to do
Thank you.
whatever you want. Sure.
Thank you very much. I probably will shoot you an email afterwards. This is really
Yeah, of course, feel free. I'll send you I'll send you not just the paper, but even the markdown notebook, actually, the source notebook that contains the code and everything, so you can start playing immediately.
Thank you very much.